Item number 5 of our problem set. In this item, we have a chemical reaction that describes how dinitrogen pentoxide is a very unstable and dangerous compound, and that its solid crystals decompose into nitrogen dioxide gas and oxygen gas. Our first task is very simple: to write down the balanced chemical equation for this process, and making sure we include the states of matter. So I've gone right ahead and typed down all the different molecular formulas of the reactant, pentoxide, and its products, nitrogen dioxide and oxygen O2. Making sure that I've also indicated that dinitrogen pentoxide is a solid, nitrogen dioxide and oxygen gas are both gases. To balance this equation, we need first to identify which element we are going to balance out first. And typically that element is an element that appears in only one compound on both sides. And that is actually both nitrogen and oxygen, but oxygen this time exists in its elemental form, and we know that an element that exists in elemental form will be balanced out last. So it makes sense to balance nitrogen out first. And that's very simple. We'll put the coefficient of 2 on nitrogen dioxide. Next, we are going to balance out oxygen by adjusting the pure element oxygen, possibly giving it any fractional coefficients. So right now, we have 5 oxygen atoms on the reactant side, and we already have 4 oxygen atoms from nitrogen dioxide, having 2 moles of it. With that, we only need 1 more oxygen atom, so we will put a coefficient of 1/2 on our elemental oxygen. In order for us not to have that fraction, we will go ahead and multiply everything by 2. So you'll end up with the coefficient of 2 on N2O4, coefficient of 4 on NO2, and a coefficient of 1 on oxygen gas. To then answer the next parts of this question, which is the kinetic part, we will shift our screen from this slide to an appropriate page. There we go. We are given the concentration of dinitrogen pentoxide, or N2O5, at different times. And these are all written down on table 1. Our first task is very simple: to plot this data on a concentration versus time plot. So what you'll do is you'll copy this data you have onto an Excel sheet, or you'll start inputting them into your scientific or graphing calculator. You will then try to create the following, making sure that your axes are pretty clear. For a concentration versus time plot, it is time that will always be on an x-axis, and it will be concentration in molarity on our y-axis. You can go ahead and even consider connecting or making sure that all the different data points are connected, since this is a continuous chemical reaction. But note that not always the case, no? That we can connect data points. Our next task, okay, is to plot the concentrations of the products of nitrogen dioxide and oxygen versus time as well. So here's the thing: how do we solve for the concentrations of nitrogen dioxide or oxygen at any given time point? The answer is in stoichiometry. We have molarity of N2O5, but we can imagine that we have 1 liter of everything. No, the entire reaction is happening inside the enclosed 1 liter container. With that, you can imagine that this molarity values will also correspond to mole values. And actually, you can do stoichiometry using molarity rather than moles. The first thing we're going to do is we are going to create a new column labeled the amount of N2O5 consumed. And we are going to solve this simply by taking or copying the initial concentration of 0.0365 molars, and we are going to subtract whatever value or concentration N2O5 exists as now. So with that, we'll just get 0 moles of N2O5 consumed at time equals 0. Obviously, at time equals 0, the reaction hasn't occurred yet. We're gonna go ahead and drag and drop the same or apply the same formula to all the other cells. So as you notice, as the concentration of N2O5 is now very small, the amount of it consumed is now very large. The amount of N2O5 consumed will then be able to be stoichiometrically converted into the amounts of NO2 and O2 produced. So we're going to create 2 columns, amount of NO2 produced and the amount of O2 produced. To solve for that, we are simply going to use the stoichiometric ratios given the moles of N2O5 consumed. So I'm going to go ahead and equate NO2 produced to the amount of N2O5 consumed. And we know that we're going to multiply that by some stoichiometric factor. We know that there are 4 moles of NO2 produced for every 2 mole of N2O5 consumed. So I'm going to multiply 4 over 2 to that and drag and drop it all the way down. We're going to do the same for the amount of O2 produced. Again, taking the amount of N2O5 consumed as our reference and multiplying it by the appropriate stoichiometric ratio. So with that, we know that we have 1 mole of O2 produced for every 2 moles of N2O5 consumed. And we're going to drag that formula down or apply that formula to all the other values of N2O5 consumed at different time points. We are then going to select all of these columns and then insert another graph. So this graph right here will showcase, okay, all the different reaction or concentrations of the different substances at different points in time. Please, again, don't forget to label the concentration and time axes. Okay, and what we're going to do is we're simply going to delete the N2O5 consumed plot since that does not concern this experiment. And now we have the concentration versus time plots of our reactant N2O5 as well as our products NO2 and O2. It makes sense that as N2O5 is consumed, no, with its decreasing values in its graph as time increases, you'll have an upwards or an increase in the amounts of both NO2 and O2 at different stoichiometric amounts. Our next question is, what is the relative rate expression for this reaction? And to answer this, you'll simply have to look at the formula for relative rate expression, which takes into consideration the stoichiometry of this reaction. So we have it here. Let me just drag it up here. Okay. We're then asked, how does our graph illustrate our relative rate expression? Okay, so we have negative 1/2 the rate of N2O5 is 1/4 the rate of NO2, and it's the rate of O2. let's look at the graph that's the steepest, and that's the graph of NO2. The reason why NO2 has the steepest graph or the highest rates at any given point is that in the balanced equation, it has the highest stoichiometric coefficient, which means at any given point in time, a lot of it is being created. And going back to our graph, the flattest kinetic curve or reaction rate curve will be that of the O2, given that in our balanced equation, it has the smallest stoichiometric coefficient. So at any point in time, very little of it is being created. And you can actually solve for just how much faster or slower each of these rates are at any given point in time by simply looking at this expression. So let's look at time equals 0, the initial rate at this time equals 0 area. Okay, we can say that the rate of O2 is actually 1/4 the rate of NO2, meaning this yellow graph's slope at point 0 is 1/4 the slope of this very steep gray graph. Conversely, we can say that this gray graph is 4 times steeper than that of this yellow plot. Or we can say that this gray graph is actually 4/2 times steeper, or basically 2 times steeper than this blue graph, should this blue graph have a positive rate, which is why we put a -1 over there. So that's comparing relative rates using the relative rate expression and being able to observe that using this plot. On to the next set of items. Okay, for letter F, we are then tasked to find the most linear integrated rate law plot. And using the data, what is the reaction rate order of dinitrogen pentoxide? So right now, we can remove the other stuff from our plot and again go back to just how N2O5 changes over time. And you can already see, even without adding a trend line, that this is not a very linear plot. It's a curved plot. Okay, we can further... Oops, sorry. We can further show that its R squared is not quite 1. So not quite very linear. We will keep that on standby. It might be a zero order reaction should this be the most linear plot, but let us test for the other possible orders. To test for a first order reaction, or N2O5 being a first order reactant, we are going to plot the ln of its molarity over time. So we're going to create this new column and simply write the equation ln, click the value of the concentration of N2O5 for that given point in time, and solve for it. Apply the same formula to all the other concentrations of N2O5 over time. And to solve for a second order possibility for N2O5, we are going to take the reciprocal of its concentration. So what we're going to do is going to simply do equals 1 divided by the value of the concentration of N2O5 at that given point in time. And again, apply that formula to all the different concentrations of N2O5 over time. We are then going to plot time, or these values against time, this time without having to put any connections between the data points. So these are now considered discrete values. Or you can be inputting these data points against time in your scientific calculators to then try to find the linear regression equations of those plots. So with that, let's just increase the font sizes so it's more clear on your screen. We get an r squared of 0.999, so very close to 1, with the natural logarithm of concentration against time. And this indicates that our reaction is in fact a first order reaction with respect to dinitrogen pentoxide. With that, we can now write the differential rate law of this reaction as rate equals K times N2O5 raised to the first power. Last, we are asked then to find the rate constant K based on your linear regression from the integrated rate law plot. Now, it is this equation that will actually guide us in finding the value of the rate constant K. Note that for a first order reaction, its linear regression, y equals mx plus b, will reflect the following equation, where y is the ln of concentration, the slope is actually negative k, and the b is just the ln of the initial concentration of our reactant. So our reaction rate constant actually comes from the slope of this plot. So here, K is just equal to the negative of negative 0.0005, or just 0.0005. Sir, what about the units? Okay, we know that rate should be in molarities per second, and we know that K is being multiplied to a molarity, which means the units for K here will be just 1/second. Let's go on to the last items. Okay. So now that we have our integrated rate law, we can then use this information to solve for concentrations at different times, or solve for how much time it will take to reach a certain concentration. In letter I, we're tasked to use the integrated rate law to then find out how long the reaction will take for N2O5 to be half of its original concentration. So, in letter I, we know that the initial concentration is 0.0365 molar N2O5, and the first thing we're supposed to do is to find out what half of this concentration is. So that's just equal to 0.5 times 0.0365. So this is the concentration in molarity that we need to find. Okay. Now, to be able to use the integrated rate law for a first order reactant, we need to remember that it's actually the ln of the concentration against time that we plot. So we have to convert this concentration to the y term, or an acceptable y term. So that will be ln of this value above. And with that, we can then plug this value as the y, and we're going to solve for x, which is the time it will take for us to reach this concentration, which is half of the original. So with that, we're going to use again the equation of the line that we have, our y, which is just this. We're going to add the intercept value of 3.3029 according to our plot. And then we're going to divide everything by negative 0.0005, or our slope. And with that, we get approximately 1,400 seconds as the amount of time it takes to reach half the concentration. Okay, if you look at the time scale that we have, everything has just two significant figures, so your final answer should be around 1,400 seconds. Let's do something similar to solve for the concentration of dinitrogen pentoxide by the 2-hour mark, or at 7,200 seconds. So our given is, again, we want to know the concentration at x equals 7,200 seconds. So all we need to do is to solve for the y term. Okay. However, we have to remember that this y term will be in an ln of concentration form and not concentration. So to do that, we'll simply apply the formula equals negative 0.0005 times our x value minus 3.3029. And that will give you this value. How do we get the concentration from an ln of concentration term? Well, we'll simply have to raise E to this value, or Euler's constant. So in Excel, all you need to do is to write exp and select the value you want to raise E to. So the concentration will be around 0.00100 molar of N2O5. And going back to our concentration versus time for N2O5, it makes sense that at 7,200 seconds, 0.00 10 could be the new concentration, a lot smaller than the concentration at 0.0064 at 3,600 seconds. With that, we've just rounded up and answered everything in our problem set. I hope this session or set of videos has been useful. Thank you.